Every movie gets this wrong: the screaming spaceship, the violent shudder as the hull buckles, the dramatic red warning line marking the point of no return, crossed in a blaze of alarms and shattering metal. It's a great scene. It's also, according to the actual mathematics of general relativity, almost entirely fiction, at least for the moment that matters most. If you fell into a large enough black hole, feet first, calm, no spaceship falling apart around you, the honest answer physics gives you is stranger and quieter than any movie would dare film. You would likely cross the single most consequential boundary in the observable universe, the edge past which light itself cannot escape, and feel absolutely nothing unusual at all. No wall, no flash, no jolt, just gravity and then more gravity, and no local sign whatsoever that anything irreversible had just happened to you. That single fact, once you understand why it's true, forces open one of the strangest and most genuinely unresolved arguments in modern theoretical physics. Here's why this question is worth taking seriously rather than treating as science fiction trivia. What happens, physically and experientially, at the boundary of a black hole isn't just a curiosity about an exotic form of death. It's a direct test of whether one of Einstein's most fundamental assumptions about reality survives contact with quantum mechanics. And for the past decade, a genuine, still unresolved paradox has forced physicists to ask whether the "nothing happens" answer can possibly be correct after all. To understand why falling in might feel uneventful, you have to start with what Einstein once called the happiest thought of his life. In 1907, while working at the Swiss Patent Office, years before he finished general relativity, Einstein had a realization that would become the seed of the entire theory. Imagine a person falling freely, he reasoned, off a roof, say, purely as a thought experiment, and for as long as that fall lasts, that person would feel completely weightless, no sensation of falling, no force pulling on them at all. From inside a windowless box in free fall, there would be no local experiment you could perform to distinguish between falling freely in a gravitational field and simply floating in the emptiness of space, far from any mass whatsoever. This idea, called the equivalence principle, became the foundation Einstein built general relativity on top of, and it has been confirmed by every gravitational experiment performed since, including the everyday experience of astronauts aboard the International Space Station, who aren't weightless because they've escaped Earth's gravity. They're weightless because they, and the station around them, are in a continuous, gentle free fall around the planet. Apply that same principle to a black hole, and something remarkable follows. An event horizon isn't a physical surface, a wall, or a membrane made of anything. It's a boundary defined purely by geometry, the specific point where the curvature of space-time becomes so extreme that even light aimed directly outward can no longer make any progress away from the center. Crucially, for a person actually falling through it in free fall, the equivalence principle says there is no local experiment, no measurement performed, using only your immediate surroundings, that can tell you the exact moment you've crossed it. There's no marker, there's no signpost. Locally, space-time at the horizon of a sufficiently large black hole can be made arbitrarily smooth, arbitrarily unremarkable, indistinguishable from ordinary empty space curving gently around you. That doesn't mean falling into a black hole is safe. It means the danger isn't the horizon itself. It's something else entirely, called spaghettification. And whether it kills you before, during, or long after you cross the horizon depends almost entirely on one number: the size of the black hole. Spaghettification happens because gravity doesn't pull on an object uniformly. The part of your body closer to a black hole's center always feels a stronger gravitational pull than the part farther away, and that difference, called a tidal force, stretches any falling object along the direction of the fall while simultaneously compressing it from the sides. For a small stellar mass black hole, formed from a collapsed dying star, this tidal force becomes lethal long before you ever reach the event horizon. You'd be stretched into an unrecognizable thread of matter while still well outside the point of no return, precisely the violent, cinematic death the movies imagine. But tidal force depends heavily on the size of the black hole itself, and here the mathematics produces a genuinely counterintuitive result. The bigger the black hole, the weaker the tidal force at its horizon. The radius of a black hole's event horizon grows in direct proportion to its mass, but the tidal stretching force at that horizon actually shrinks as the black hole gets larger. For the supermassive black holes found at the centers of galaxies, including the one at the heart of our own Milky Way, weighing millions or billions of times the mass of our Sun, the tidal forces right at the event horizon can be so gentle that a falling human being would notice nothing unusual whatsoever, crossing the boundary in total comfort. Spaghettification only becoming a concern much later, deep inside, as they continue falling toward the singularity at the center. This produces one of the most genuinely bizarre facts in astrophysics. The small black holes, the ones that seem more survivable simply because they're less imposing, are actually the violent, instantly lethal ones. The largest, most imposing black holes in the universe, the supermassive giants powering entire galaxies, are, right at their boundary at least, the gentle ones. There's a second layer to this story that makes it even stranger, and it involves what an outside observer would actually witness while all of this is happening. From your own perspective, falling in, your personal clock, what physicists call your proper time, keeps ticking normally, and you cross the event horizon in a finite, ordinary amount of time, feeling nothing remarkable as you do. But someone watching you fall from a safe distance would never actually see that crossing happen. Because gravity slows time more severely, the closer you get to the horizon, your image, as seen from outside, would appear to move slower and slower, your light becoming more and more redshifted, stretching toward invisibility, until you appear to freeze, fading gradually into darkness rather than visibly crossing any boundary at all. In the purest sense of the mathematics, an outside observer watching forever would never see you complete the crossing. You, meanwhile, would have already crossed and kept falling, entirely unaware that from the outside universe's point of view, you'd become a fading, frozen image lingering at the edge of visibility forever. Two completely different, equally valid descriptions of the exact same event, a direct, visceral demonstration of one of general relativity's strangest lessons. There is no single, universal now that everyone agrees on. For decades, this entire picture, a smooth, uneventful horizon crossing, followed by a much later, more dramatic ending near the singularity, was the accepted physical intuition among physicists working on black holes. Then, in 2012, 4 physicists, Ahmed Almhairi, Donald Marolf, Joseph Polchinski, and James Sully, published a paper that seemed to prove this intuition couldn't survive when you took quantum mechanics seriously. Their argument, now known as the Firewall paradox, showed that 3 separately reasonable assumptions about black holes cannot all be true at once. The first is unitarity, the quantum mechanical rule that information is never truly destroyed, which requires that late-emitted Hawking radiation be strongly linked, or entangled, with radiation the black hole emitted much earlier. The second is the equivalence principle itself, the smooth, unremarkable horizon we just described, which requires that same late radiation instead be entangled with whatever lies just inside the horizon, so that a falling observer encounters nothing unusual. The third is a basic rule of quantum mechanics called the monogamy of entanglement, which states that a single quantum system cannot be fully, maximally entangled with 2 separate independent systems at the same time. Almhairi and his colleagues showed that for an old black hole, one that has already radiated away more than half its mass, you cannot have all 3. Something has to give. And if it's the smooth horizon that breaks, the mathematics suggests an infalling observer wouldn't experience a calm, gentle crossing at all. They would hit a firewall, an intensely energetic barrier of high-energy quanta, sitting right at the edge, destroying them instantly, contradicting everything the equivalence principle had promised for over a century. This is not settled. It remains one of the most actively debated results in theoretical physics. Some physicists argue the paradox reveals a genuine breakdown of one of these 3 assumptions. Others argue it reveals limitations in how physicists have been mathematically describing quantum information near a horizon rather than a literal wall of fire waiting for anyone unlucky enough to fall in. The 2019 breakthrough involving islands and replica wormhole calculations, the same research that helped resolve the broader black hole information paradox by showing information can escape encoded in Hawking radiation without requiring destruction, has offered physicists new tools suggesting the interior of a black hole may be reconstructible from its radiation without literally duplicating information in two places at once, potentially diffusing the sharpest version of the firewall argument. But a fully agreed-upon resolution, one that every theoretical physicist accepts without reservation, does not yet exist. It remains genuinely open. A separate, competing idea, the fuzzball proposal developed largely by physicist Samir Mathur, sidesteps the firewall question in an entirely different way. It suggests there's no traditional sharp horizon at all, and that what you'd actually encounter falling toward a black hole is an enormously complex, horizonless quantum structure, extending roughly to where the horizon would otherwise be, subtly encoding the black hole's information directly into its structure. In some versions of this picture, crossing into a black hole doesn't feel violent, but it also isn't quite nothing either. You'd be gradually, imperceptibly converted into part of that structure, information and all, without ever noticing the transition happen. None of this has been, or currently can be, tested directly. No probe has ever been sent toward a black hole's horizon, and by the very nature of what an event horizon is, no signal describing what an infalling observer actually experiences could ever be sent back out to confirm it. Everything here rests on mathematics, extrapolated from theories that are extraordinarily well tested everywhere else, applied to a regime no one has ever been able to observe directly. So, what does it mean that the most catastrophic-sounding object in the universe might, for the most consequential moment of your entire existence, feel like nothing at all? It means the drama humans instinctively attach to black holes, the violence, the crushing finality, the sense of a boundary that should announce itself, may simply be a failure of intuition, built for a universe of walls and cliffs and edges you can see coming. Reality, at least according to Einstein's own foundational insight, doesn't work that way at the edge of a black hole. Gravity, taken to its most extreme limit, can behave gently, precisely because it behaves everywhere the same way it behaves on your falling elevator, on your orbiting space station, on the ordinary ground beneath your feet right now, and it means that somewhere underneath that apparent calm, an entirely different battle is quietly unresolved. A genuine, unanswered argument about whether quantum mechanics permits that calm to exist at all, or secretly replaces it, for anyone unlucky enough to actually test it, with a wall of fire no one has ever mathematically agreed on how to avoid. You may never know, until the moment it no longer matters, which version of that story is true. The deeper we look into the universe, the more it begins to look back at us.